We're going to look at a couple, kind of special or different scenarios for circular motion now. The first thing we're going to do is we are going to look at what happens when things are going in vertical circles. And I mean, but we're talking about, you could do this already, but we're going to do it when we are talking about something that is moving on a non-rigid structure, like you're swinging something in a rope or something like that. And if you're swinging something in a vertical circle on a rope, you can't just swing it any speed you want, because you have to swing it fast enough in order for it to make it around. And what happens when you swing something in a vertical circle, like you think about like spinning a rope or something like that, or a bucket or something like that, it feels different at different locations. So of course the classic scenario that's really common like for kids is when they're, you got like a bucket of water or something like that, and you're whipping around this bucket of water. Or someone's like a bucket of sand or something at the beach. And depending on where the bucket is, like you'll feel it pulling with different amounts. Like certain parts it feels a lot heavier, it feels lighter, that type of stuff. And these are the kind of vertical circles that we're talking about. Now, you can't just spin at any speed you want, because if you spin the bucket too slowly, the water is going to come crashing down on you. And sometimes, you spin it so fast that the handle might break. And it depends on the location of the object. You'll feel different things in your arm depending on where the bucket is. And the same thing applies for vertical circles like this, or things like roller coasters going in a vertical circle, or any kind of like carnival rides and that type of stuff. Vertical circles are just it's still circular motion, but there's some special things that we can look at in terms of location and what's going on at different parts in the circular path. So we're going to look at vertical circles a little bit, and we're talking about going around, obviously, but there's like no rigid structure holding it. So we're going to use things like like ropes and stuff like that. So you can feel differences, and the system might fail and that type of stuff. Okay, because if it's on a rigid structure like in a post, you can go any speed you want. The post isn't going to like buckle at the top or something like that, but a rope or a chain or something like that would. So that's sort of like the idea behind what we're looking at. So let's look at something really, really simple here to sort of map things out a little bit. I'm just going to draw like a little circular type path, maybe something like this. Okay, there we go. That's not too bad. And we'll make this a little bit smaller, so it's like the back part of the circle. Ooh, that's close enough. All right, so and then we'll have a mass of some kind, and it's on a rope of some kind, and it is whipping around. Okay, something like this, and then it goes around back this way, behind, and then back at the top. All right, so something like this. So there's different places that we can look at and analyze and see what's going on. Now, when you are whipping something, you guys probably remember doing this when you were kids, there's different places that feel different. And the place where you'll feel like the most pull by far is typically at the bottom. Usually it's at the bottom. This is where you will feel the most pull. And you typically feel the least amount of pull at the very, very top. And those are like two critical locations that we can look at. Now, let's sort of look at what's going on in terms of the forces. Now, there's a couple forces going on. Obviously, we have FC. I mean, there's no question. So we can take care of that. FC always points to the center of the circle, no matter what. So FC is pointing to the middle, top and the bottom. But another critical force here is gravity. Gravity is actually helping you out sometimes, and sometimes it isn't. And if we look at gravity a little bit, if we go to the top, gravity obviously is pulling down, and here, of course, force of gravity is also pulling down. So let's see what's going on. Well, if we go to the top, let's just start with the top part. If we go to the top of the circle, we need a certain amount of FC in order for it to go around. And FG is actually pulling in the same direction as the FC. So actually, the force of gravity is actually helping you at the top. So maybe you need 10 newtons to go around. You need 10 newtons of FC, and gravity is supplying 7 of them. Well, then you only need to supply 3. Gravity is actually helping it go around. So what you feel, of course, you guys feel the force as as tension, the tension you guys would be the difference between the two. So you need the FC to go around, but FG is helping you. So we can subtract how much FG is helping you with in order to find out how much you'd have to pull with. So then what about at the bottom? What's going on here at the bottom? Well, at the bottom we sort of got the exact opposite actually happening. So at the bottom of the circle, first of all, gravity is trying to pull it down. So you have to pull up at the bottom of the pathway. You need to pull up just to hold the bucket up. But then not only do you have to pull up with enough force to cancel gravity, you also need to then pull up with enough force for it to go in a circle. So instead of you feeling the tension of the difference between the two, that is where you would actually add them instead. You will feel the sum of those two forces at the bottom because you got to cancel out gravity plus pull up with even more for the FC. So in the top, it always feels the lightest, and the bottom, it always feels the heaviest because one place gravity is helping you out, and the other place it is actually fighting against you. Now, everywhere else in transition between every place from the top to the bottom, the angles change and FG is always helping you out or fighting against you, except for one place. The one place where gravity doesn't matter is right in the middle. Right there in the middle of the pathway on both sides, that is the one place where the tension is actually equal to FC, because FC would be going to the center of the circle. In this case, this will be like sideways. Gravity would be going down. Since those two are perpendicular to each other, you wouldn't actually be helping, or FG is not helping you, FG is not fighting you, so all you would feel is FC. And everywhere in between would be a transition between the minimum tension at the top and the maximum tension at the bottom. Now, the other part that kicks in is if the system is going to fail. What if you're not going fast enough? Typically, when you're a kid, you got the bucket of water or sand. You try and go slow as you can without the circle just falling apart. And if it's going to fall apart, it's going to be at the top. You need to go fast enough for it to go across the top. And if you remember playing with this when you're like doing stuff with it when you're a kid, when you're going really, really slow, as you go slower and slower and slower, the tension actually becomes smaller and smaller and smaller. In fact, when you're going slow as you possibly can, when you're at the top of the circular path, you won't actually feel anything. So when you are at the minimum speed that you can go, and the top is that's the critical part right there, is the top of the circle. When you're going slow as you possibly can, then the actual tension is equal to 0 because gravity is supplying all of the FC. All right. So when that occurs, the FG is actually supplying the FC. So those two are going to be equal to each other. Clean it up a little bit. There we go. So FG and FC are equal to each other, and gravity supplies all the FC that you need. So with that, mg would be equal to mv squared over r, and the masses actually cancel out. So it's kind of neat because it doesn't actually matter how heavy the object is. It's actually the radius of the path that actually dictates how fast you need to go in order to make it around. So this would be v min right there. And then we just, rearrange a little bit, and you'd have v min would be equal to the root of gr. So it's kind of neat. Like it doesn't matter how big you are, how small you are, how massive the object is. It's all about radius. So every specific radius has a minimum speed that's needed in order to make it around. All right, and of course the bottom, you're always going to be going fast enough at the bottom to go up. That's no big deal. But one of the things that happens at the bottom is, since the tension is so high, if like the rope is going to break or the handle in the bucket's going to break or something like that, it's typically going to break at the bottom when the tension is the highest. All right, so these are some of the mechanics that go along with a vertical circle. All right, so let's look at a vertical circle scenario and sort of see how these things can work together. Okay, so let's get rid of this. There we go. We'll delete that. Okay, so let's just draw a person here. There we go. Have a person. All right, so let's just say they're whipping something around in a circle here. Okay, let's say it is a, I don't know, something like that. Okay, let's say they got like a giant coffee crisp bar on a rope. Why? Who cares? There we go. All right. Okay, so let's say we have a 2.3 kilogram coffee crisp bar, and let's say that it is moving along and going in a vertical circle as shown. And let's say that it is whipping around at 4.2 meters per second. Okay, so let's look at that a little bit. Well, let's say at the top of the loop here, at this location, let's say the guy is feeling 50 newtons of tension. And let's find out what is the radius of the path. Okay, let's just start by finding simple forces. I've got the mass, so the force of gravity is going to be really simple. So let's do the good old mg for that, and we've got about 22.6 newtons of gravity. And at the top, gravity is actually helping me out at the top. So he feels 50 newtons of tension. So he's pulling down with 50 newtons of force. Gravity is also pulling down with 22.6 newtons. So I'm going to put those two together, and my FC would then be 72.6 newtons. So there's a FC of 72.6. The guy's supplying 50 newtons, gravity supplying 22.6 newtons, so it's got to put those two together, and the FC's got to be 72.6 newtons altogether. And of course, this has to be equal to the mv squared over r. I've got the mass, I've got the v, I can just rearrange this, and I can solve for my radius of my path. Okay, so I do that. My radius will be it should be around 0.56 meters, so just over half meter long rope, and that is what he is whipping around over there. Okay, all right. So let's. He's easily making it around the circle. So what if he wasn't making it around the circle? What would be the minimum speed required to get around? Well, then of course, the force of tension would be 0. You wouldn't feel anything at the top. So that again tells me that my mg would be equal to my mv squared over r. And of course, those cancel out again. So my v min would be the root of g times r. So again, it's all dictated by the actual radius of the path, not the mass itself. And if we calculate that, we can get a V min of around 2.34 meters per second. So 2.34 would be the minimum to go around. This one's going around at 4.2, so it easily makes it. Okay, so at the top, gravity's helping you out, which of course reduces the tension. And of course, at the bottom, you'd add the mg and the tension together to get the FC. Oh, no, so I mean subtracted to get the FC, right? So there's a basic example of how this works, and it's no real difference, just the varying tension. Typically, we've had a constant force going in our circles, and here the FC, we're not really changing the FC. It's more about what you feel changes from one location to the other. All right, so he's got to look, is it more tension, less tension, top or bottom, gravity helping me out, gravity not helping me out. And it's not super strange or complicated, and you just sort of